Good afternoon, YouTubers. Today we're going to be working on this steam engine model. And the main point is, anytime I design some of this steam engine, this is SolidWorks, by the way, and I just put them together without having really a blueprint. So sometimes the main point is, what would be the power that you can extract from these tiny engines, and people have asked me that before, because I have put some of this design with my YouTube channel. And so the idea is, how can we go and based on on the supply of steam or air, depending on what's the case, because mostly my design are for 3D printing. And so I will put air here at a given pressure. This is the valve, and that has an eccentric on this size for controlling the input of air at a given pressure. And so this is what's going to happen. But when I'm putting this together, one of the problems that I always have is, what should be the weight of this guy, of the flywheel? Never have a good idea how to to decide how much kilograms this flywheel should weight. So that's a problem. And the other one, which is easier, is how much power can I extract from this tiny engine, according to perhaps the radius up here of the crank arm, the arm here, and the diameter of the piston, as shown here. If I move this, let's see, you can see it right there, right here. And and depending on the pressure, so several parameters that you need to have them well defined in order to know what's the power that you can extract from this tiny engine. So to do that, let's go to Excel and figure it out. Let's go here. I'm in Excel, and I have two ways to do that, to understand these small engines. And basically, one is called plan, and the other is piston crank mechanism. Plan, P-L-A-N, actually stands for, the letter are the only thing that you need to do some estimate of the horsepower of that steam engine or air engine, whatever you're doing. Like, for example, the pressure at the pressure of the chamber that you will be working, 10 psi. The stroke length here is about 2 inches, the stroke, and it's only one way, so it's single acting, not double acting. This is single acting, so the stroke is 2 inches. When for example, if I choose this one here, the way that this piston will move down will be 2 inches, because basically the radius here, the R, is about 1 inch. So that's basically the idea here. So you have about, the stroke length is 2, and piston diameter that I'm using for my design is about, pretty much always is about 1 inch. Can make it larger, but that will, for 3D printing, that would take forever. And so the area of that piston is about this, and so you multiply the area by the pressure, you have force. Basically, that's what's happening. Now continue with that. Then you need you have the P, the L, the A, the P, the L, the stroke length here. Let's put down L here so you know what I'm talking about. The area, I should have to down this in calculator, and the RPM, N. So you multiply all those numbers, eventually you get power. Now the unit for power there, when you multiply 1, 2, 3, this 4, that P, L, A, and N, end up being pounds per feet per minute on that type of unit. Then you want to convert that to second, pound per feet per second. So you divide this number divided by 60 and you get it by second. Now you take this number and divide it by 550, then you get the horsepower. And here's the horsepower. This number, I know, is just very tiny. That my design for extracting energy is pretty much negligible. It's very small. It's only for demonstration purposes. But that's the idea. And this number being in horsepower, I know that it's small, but I don't have a clue how small it is until I convert that to watts. It's about 9 watts. So you take this number, apply that horsepower by 746, and you convert that to watts, and that's how tiny it is. 8.87, not even 10 watts. That's basically that design. Now, very important, eventually you would like to know the torque. I have the torque here in this unit, pound per feet, and the torque is just basically one of those formula you can get anywhere for horsepower for an engine, and that in this case the 5252 is just for the collection of unit, as long as you use the B10, and B10 is the horsepower and the B7 is the RPM. You get those units the way they are there, eventually you hit the pounds per feet. Well, that's so again, what you're gonna get with plant is basically that you have a very tiny engine that at that particular pressure of 10 psi, the amount of energy that you can extract from it will be pretty much useless, about 10 watts. That's not a big deal. Now, if you change the pressure, let's say to like a train, like a steam engine train, and get that to about 200 psi, then we're talking something else. Obviously, still it's very small piston diameter, about 1 inch, but now it increases to 177 watt. That's considerable. Now, if you know, as we are talking about this, if we change the piston diameter, let's say to 3 inches, now we have a 2 horsepower engine. That's a whole different game. I mean, I will say this is just professional level when you start to talk about higher than, I would say, 0.5 horsepower. That's a lot of power that you're talking about, and with that amount of power comes also, like for example, a boiler, a proper design of a boiler, and eventually you become a full mechanical engineer in order to get this right. But if you are in amateur level and just want to do some 3D printing and have an idea of what's going on, then let's go back to put this number where they should be, about 10 here, and no more than 1 inch here. That will do, and we are back again to a more small engine, about 10 watt maximum. All right, that's good, but this part here will not solve, for me, will not solve the issue that I'm talking about here, which is, let me go back here, right here. That will not solve the issue of how much this flywheel should weigh to get this job done. Yeah, it's always, I'm guessing, and I know that as I make this flywheel heavier, as I go along, you know, put some bolts right through them, and I'm sure that this flywheel is balanced, you get the job better. But never have a good idea of what, you know, for my design, what would be the weight that I need to look for. So in that case, that's when the second part of this table in this Excel, the piston crank mechanism, become very important, because the main idea is to generate a curve. Let me see if I can get there. A curve like this, what is called the turning moment diagram. If we can get that, then we can eventually get and obtain the amount of mass, the kilograms that I need for my flywheel as for some dimension that I already set up. You know, whether you want a flywheel of 3 inches diameter or 5 inches diameter, you know, it's up to you. But that's the idea. The idea is when you set the diameter of your flywheel, then what should be the weight, right? And for that, we need to generate this turning moment diagram, which is straightforward if you follow what I'm doing here, basically. Like for example, there's some dimension that I extracted here from this side, from what is called the plan. Let me put this where it should be. Let me get this smaller, perhaps a little, so I can see more. There we go. So this is what I'm saying. From the piston-crank mechanism, you have the R, that's about 1 inch, and the L, this here, is about 0.1 of a meter, or about 100 millimeters. And the RPM again is the same that I have here. It's about 300 RPM. That convert that to radians per second. That end up being about 31.4. Not, I mean, I don't have any more number than that, so that's how you do it. And the pressure is going to be the same pressure as here. So I'm using 10 psi of air. Now that air is important. I'm not allowing that air to expand. So in other words, the pressure will not drop. I want to keep the 10 psi all the way down to the, you know, the last second, even a fraction of a second, because when this get there, all that air need to escape so that the piston can go up back again. But the main point is that that 10 psi is available all the way. I'm not doing any cutoff here in this design. Now that's the pressure. The piston diameter is still 1 inch, no big deal. Then we get the area as we did back here, and from that area we get the force. That will be multiplying 10 psi, 10 pounds per square inch by this 0.78. Eventually we hit the 7.85 pounds. We convert that to Newton because basically I'm going to be using a metric system mostly for my calculation, make life easier. So Fg, which is this Fg here, is about 35 Newton. Now I know everything that I need here on this equation. The only thing that I need to do is move the t, you know, and that will allow me to move this the crank at a given time, so it will start to rotate from 0 to 360. So when a full turn. Now if you do that, eventually what you have to do is take this equation the way it is here, and for example I have time here, and I have the delta t that I'm going to be using is 0.001, very small because this is very fast, 0.01. Now for the torque, it's basically take this equation the way it is and write it down here, and I'm not going to put everything, you know, so I'm going to go. I don't want to go through it, you know, with all the details, but you get the idea of what you need to do. The important part here is that the time comes from this column, and F double phi is the rad per second. So that's W, and W times T allows then this to rotate, and W times T is actually then the angle, which is in rad here, radians. All right. So basically then you have in this table you have time, torque, angle. I also can calculate this angle here if I want to. I already did. It's right here. It's called phi. Now there's another 3 column here. One is called the differential torque, and another is called energy, and another is called total energy. Let's start by total energy, the last one here. The total energy is the energy under the whole under the curve, under the blue curve, all that area. Eventually from that total area you can get then the mean average torque, which is coming from the red line. Notice what I was saying, that this engine is a single stroke, meaning that you only see this like this, because it's a double stroke. Then you will see another one coming up like this, so you will have 2, but in this case it's just one and then another. But in this case it's just one single stroke. That's it. That's what you get, and that's where you get this type of curve. And now this curve should have enough energy to compensate for where there's no energy down here, and that's what the mean dropped down to here. All right, so how can we calculate the mean out of this curve? Remember, the blue curve comes from a plot of torque, which is this column, versus angle versus radians down here. So you touch it, that's where it comes from, torque and versus angle. All right, now for the area of under the curve, is as simple as just kind of a trapezium rule, very straightforward. Let me see right here. So you take this high plus this high and divide by 2, so that's called the trapezium, and then multiply by the distance between this and this. That distance, the difference, that's the delta in radians for that kind of a, I would say, trapezium that is formed right here at a given height versus another height. So it will form a trapezium, and that's the area. So what's going to happen is that every time you walk here on time, you have a different trapezium, and you just add it to the other one, to the one before, and keep adding. So, but again, these are individual trapezium, all calculated. So you add them at the end. So you see, until you hit again for example here at point 1, which is 3.14, which actually is half of a cycle. Eventually it closes here, and since you don't need to worry about there's no double acting, this is not a double acting steam engine, so you at point 2, and that's the 6.28 that you see here, the 2 pi. Eventually you're going to be on 0 back again, which is what it is if you take a look to the curve as shown here. So with that in mind, then what's going to happen is from there you get the, let's see where we are here, the average torque will be let's see, mean torque is the sum of everything, of all the value here on K, and that divided by 2 pi. 2 pi divided by 2 divided by pi. 2 pi because that's from here to here, and the mean will come out from there. That's the mean torque is about 0.28 31. That when you convert that torque into pounds per foot, or in this case per feet, end up being about 0.2083, which is exactly the number that we got from the plan calculation. So that we are in the right track. Now, how to estimate the issue here? How to estimate the in this case the flywheel weight? How much you need to weigh? In that case, we go back again here, and this is the part that is very interesting from the turning moment diagram. The excess, this excess here, the one that is above the red line but below the blue line, that area there is the maximum amount of energy that is available to speed up the flywheel as it gains speed. Now, what's that area? That area is between this point here and this point here. So to get that area accurate, it's just as simple as going here and check where is where this happened. In other words, where is the point on the blue curve? Where's the point 28? And that point 28 is somewhere here. I approximate that value, that's around here, about 0.0008 of a second. That's where this happened. Now with that, then you move here, and eventually that's a 0 amount. There's no difference between the blue and the red. Now as you move down, that's when you start to see the difference, because you're moving down this way, then there's a difference between the blue and the red, and that's you are taking what is the height between the blue and the red. That height is the one that you will use to create your trapezium for the area, and that's where the energy eventually will come out, because basically you sit here, you will see that I'm taking this high plus this high, I add them up. Let me get it here. Right here, I add them up, this plus this, added divided by 2, and then multiplied by the difference of the rad, which is going to be this minus this, and that gives you the area of that first trapezium. And you do that, you know, across all them until eventually it goes back to see, keep going here up to when you are basically you are here. Sorry for that interruption. You are right here, and there's nothing more yet you want to do up to here. That means that when the blue curve come back to approximately 0.28, let's go back here, right here, 0.20, 39, 31, 29, 27, it's just below 0.28, so I end up here. So that's basically it. So this column J has if I add each one of those point there, this, and you add it like a sum, that sum is this point here. That's the maximum energy. This is the maximum energy that you are considering. That maximum energy is the one that we're gonna use and plug that in this equation, and we're gonna solve for the mass. As simple as that. Now, what is the fluctuation that you want to, you want to have in this flywheel? How much fluctuation? Well, let's make that fluctuation small. Small will be like a 3%. Well, let's start with 25%. Now, 25% based on a flywheel of a given dimension. Like for example, this flywheel, the flywheel radius here is about 4 centimeters. 4 centimeters, meaning about 8 centimeters in diameter. That's 80 millimeters, and basically that's about 3 inches. 3 inches is my flywheel diameter. And how heavy can I make a 3-inch flywheel? Can I make it as heavy as 2.52 kilograms? That's heavy. We are talking about basically 5 pounds of material and obviously if I'm doing 3D printing a flywheel will not make that weight. Will never make that weight. So the flywheel gotta be something else, and that's always a problem for the design of the flywheel, which is heavy enough that get the job done. Now, if I make the coefficient of fluctuation larger, I don't know, like 100, that's huge. Then the flywheel can be very light, 0.63, about a pound, or 630 grams. That could be done at 3 inches. Remember, the diameter is about 3 inches. Now, if I go back to SolidWorks and step here, now I'm here in SolidWorks. This is the original design. This is not the assembling part, but just the parts all put together, and I have all the part here for each one. Now let's check on the flywheel. The flywheel material, you can pick it up and say, well, let's make a plain carbon steel. I'm not. Let's see what it picked. Did I pick the flywheel? Let's see. Going back here, flywheel material, plain carbon steel. There we go. And now, with that said, what's the weight of that guy? Again, that guy is about, let's see where we are here, 80 millimeters in diameter. And so again, that's about 3 inches. And let's check the weight. The weight for that guy, evaluate, and let's go mass. Let's clear this. And let's go for that guy. It's about 646. The way it is right now, if I do carbon steel on it, it's gonna weigh 646. So, in other words, my 3-inch flywheel diameter better be of a material different from plastic, just to get a good job. In that case, like I don't aluminum would not be that heavy either, so I'm not sure. Maybe aluminum would not work. It's easier to work with. You can do some forging with aluminum, and but I don't know. Let's see. Let's pick aluminum just to entertain that flywheel material again. Let's see. Material. Edit material. Aluminum alloy. 6061. Apply. Close. And so let's check the weight, mass property, clear. That's the problem. 223 grams. In aluminum will be too light. So 223 grams has to be heavier than that. So I'm thinking about it. what can I use just to make this flywheel heavy. You can put some bolts, put some bolt here just to make it heavier or something like that. I don't know, maybe. The idea is that now you have a way to decide whether your flywheel will be or not, as for the design purposes. So going back again to Excel, and that's at 100%. I'm not, that's 630. I definitely would like to get this number to get smaller. I would say 50%. That would be, that's a lot better. But then I need about almost 2 to 3 pounds of material of my flywheel mass. But anyway, the idea was, how can we design a 3D printed engine and get away with with a flywheel? And the idea is this: you have two alternatives here. The planned alternative will give you the horsepower that engine is producing, but it also produces, it will give you the torque. Okay, no problem there. But then you have to go here to the piston crank mechanism to try to understand how much energy above the mean line you're gonna get, because that's excess of energy, or this maximum amount of energy. The one that would between the blue and the orange line is the one that will provide that excess of power, or power available, maximum power, just to solve for this equation for mass, depending on what the fluctuation of speed you want. So that would be 50% at 50% fluctuation of speed. And in order to explain a little bit better of what this coefficient of fluctuation means, I did these two calculations here, which is called N1 and N2, are the two potential RPMs changes that you will have kind of a maximum RPM and a minimum RPM. So you add these two together, divide by 2, that's you're gonna get back the 300. Like, for example, as the coefficient of fluctuation gets smaller, let's say 1%, very small, you can see that these two values are very close to 300. You see, obviously if I hit 0 here, then you're gonna get the 300, and there's no coefficient of fluctuation. But again, that's not the case. So I have to have something here. Let's say that a value 25%, maybe that's gonna be okay. 25%, that's gonna be kind of a doable. Still kind of high, so maybe I need to go 50%. 50% is 1 kilogram, so I will have a very fast RPM of about 375 and very slow coming back. This part here is going to be very slow, but this part here is going to be very fast at 375 RPM. Still too much of a flywheel mass here. I'm not sure if I can get that amount of mass. So I might go, let's say 100 here. At 100, that's doable. That's 630 grams. If I do the flywheel in metal, like a cast iron or something like that, that's doable. For the size that I'm looking, very small size, about 3 inches, perhaps, I don't know, about half an inch in thickness and so forth. So, I mean, this is doable. 630 grams, no problem, looks good. Although obviously the RPM would be very different, like very high here and very 150 coming down, and the average then that's going to be the 300. So that's basically the idea here. Again, when I go to SolidWorks and I design on an engine, you will see I will try to post some on my description here, some of the early design that I have done. And I go without blueprints, so I put them together and just check them out. So and then you start to change parameters here and there and find out what's better for you. But the point is, you need to know a little bit about what you're designing, how much energy you are planning to extract, like what's the power that you can extract from this type of engine. Small, obviously. You are not powering the house, not at all. But it's a good reference to start with on your design. So and that's very simple by using this technique here called the plan. And with the plan you can get pretty decent numbers very quickly. Now, if you are more interested up to the flywheel design, then you need to go to the piston crank mechanism, because you need this. Definitely, you need this turning moment diagram. Without it, you cannot do much about it. With that, then this maximum amount of energy available here, this area will help you out to get the mass for your flywheel, depending on the size, the diameter. This is, in this case, K is radius, and radians per second, square, remember those square, and the fluctuation of speed. And depending on that fluctuation of speed, for example, if I decide 100% of fluctuation of speed, that means that I can have a maximum RPM of 450, then a minimum of 150, which is okay. I mean, this is a very tiny design. I don't see a problem in that. But if I doing like a generator, sticking this engine to a generator, that's bad, because when the generator is at the high speed, it will power the light very strong, but when it comes down to here, to the kind of the weak spot, then the energy that will not be that great. So depending on what the purpose of what you're doing, that depends on the type of flywheel that you will be using, how much mass. But again, even at this tiny small engine, you can still get into those numbers when you are, remember, this is kind of amateur league. When you go to the professional league, then perhaps this might change. The turning moment diagram will change, because you have like power down and power up. So you have this curve will be twice, because it's a double stroke, and here is a single stroke. And because that's mostly what I design, very straightforward, to put them together on SolidWorks and then do some 3D printing on them, and get an idea of what they will do. Again, nothing more to say. As always, have a great day. Bye.